You ever look at a bridge or even just a simple bookshelf and wonder what's really holding it all together? Well, the answer is this incredible invisible battle of forces happening deep inside the material. And in this explainer, we're going to give you the X-ray vision to see that battle for yourself. Look at any structure around you right now. The real question isn't just that it's standing up, but how? What's going on inside? What are the internal stresses doing? And maybe more importantly, if you pushed it to its absolute limit, where would that single weakest point be? That's exactly what we're here to figure out. All right, so here's our game plan. We're going to start by really understanding that internal battle of forces. Then we'll get to know our two main tools for this job, shear force and bending moment. After that, we'll actually learn how to draw a map of these forces. And finally, how to use that map to find the one critical spot that's most likely to fail. So let's kick things off with the battle inside the beams, because as it turns out, even the most basic-looking piece of a structure is just a hive of activity the second you put any kind of load on it. Think about it like this. You put a heavy book on a shelf. That weight is an external force pushing down. Now, for that shelf not to just snap in half, the material inside it has to fight back. It has to create its own internal resisting forces. And the entire goal here for an engineer is to map out this invisible tug of war to make absolutely sure the internal good guys are always stronger than the external bad guys. Okay, so our first tool for seeing these hidden stresses is something called shear force. This is going to help us understand one of the two main ways a beam can fail. Now, I know the textbook definition sounds a little dense, but the idea is actually pretty straightforward. Just imagine you take a knife and you slice through the beam at any point. The shear force is just the sum of all the up and down forces on one side of that cut. It's the net vertical push or pull that the other side has to resist to keep from sliding apart. And this is the perfect way to picture it. Shear is that internal stress that's trying to do this exact thing, to make one part of the beam slide right past the other, vertically. It's a slicing force, just like a pair of garden shears cutting a branch. Now, to map this out, engineers need to be speaking the same language. So we have what's called a sign convention. If the forces are trying to spin a little piece of the beam clockwise, so up on the left, down on the right, we call that positive shear. If they're trying to spin it counterclockwise, it's negative. This is absolutely crucial so that any engineer anywhere in the world can look at the same diagram and understand it perfectly. Okay, on to our second tool. And you're going to want to pay close attention here because this one, the bending moment, is very often the force that decides if a structure stands or if it fails spectacularly. So just like we did with shear, we're imagining a slice in the beam and we're adding things up. But this time, we're not just adding up the forces, we're adding up the moments, which is just a fancy word for the rotational or turning effect of those forces. A bending moment is basically a measure of how much a beam wants to bend or twist at any given point. And that snapping analogy is just perfect. Seriously, if you bend a plastic ruler, you can feel that resistance in your hands, right? That resistance is the internal bending moment fighting back. As you bend it, the top gets squeezed together, compressed, and the bottom gets stretched apart, put into tension. The bending moment is the number we use to measure that internal struggle. The sign convention here is actually really intuitive, which is nice. If the beam sags downwards, kind of like a smiley face or a U, we call that a positive bending moment. If it bows upwards, like a hog's back or an arch, we call that negative. So just remember, sagging is positive, hogging is negative. All right, enough theory. Let's make this stuff real. We're going to take these two big ideas and actually create a visual map, the shear force and bending moment diagrams for a classic engineering problem. So here's our setup. It's as simple as it gets. We've got a beam just resting on two supports, one at each end, and we have a single force, which we'll call P, pushing down right in the dead center. Just picture one heavy person standing in the middle of a wooden plank. We're going to knock this out in 3 simple steps. First, we have to figure out how hard those two supports are pushing back up. Then, we'll draw the shear force diagram, and finally, the bending moment diagram. Let's do it. Okay, step 1 is all about balance. The beam isn't flying off into space or crashing through the floor, right? It's in equilibrium. That means the total force pushing up has to exactly equal the total force pushing down. And since our load P is perfectly in the middle, the two supports just share the job equally. Each one pushes up with a force of P divided by 2. Simple. Now let's draw the shear force diagram. We always start at the far left. The instant we get on the beam, that left support reaction shoves us straight up to a value of positive p/2. Then, as we move along the beam, nothing happens. It's just a constant straight line, until we hit the middle. Bam! That big downward force P knocks us straight down all the way from plus p/2 to minus p/2. Then, we just cruise along at that new level until the very end, where the right support pushes us back up to 0. And now for the bending moment diagram. And here's the really cool part. It's built directly from the shear diagram we just drew. See that positive rectangular area on our shear diagram? Well, that tells us the bending moment is going to climb in a nice, steady, straight line, all the way to a peak right in the middle. Then that negative rectangular area tells us it's going to drop, again, in a straight line, all the way back down to 0. You end up with this perfect, clean triangle. So we've drawn these diagrams. They look kind of cool, but so what? Well, this final section is where it all clicks. This is where we connect these maps to the actual real-world strength of the beam. This right here is the single most important takeaway from all of this. Just look at the two diagrams we drew. Where does the shear force diagram cross that 0 line? Right in the middle. And where is our bending moment diagram at its absolute highest peak? Right in the middle. That is not a coincidence. That is a fundamental law of structural mechanics. And that peak value, that absolute maximum bending moment, can be calculated with this beautiful little formula, the load P times the length L, all divided by 4. This one number, M max, tells an engineer everything they need to know about the maximum snapping stress that this beam is feeling. And that's why we do all this work. That peak on the graph isn't just a number. It's the bullseye. It is the structural weak point. It's the exact location that is under the most strain from that snapping force. If this beam is going to break, it's going to break right there, in the middle, where that bending moment is at its peak. This is the spot engineers have to design for. So let's just recap the X-ray vision we've unlocked today. You can now actually visualize that invisible war happening inside of structures. You got an intuitive feel for how shear force slices and how bending moment snaps. And, most importantly, you know exactly how to find the weakest link. You just look where the shear is 0, because that's where you'll find the maximum critical bending moment. And that leaves us with one final thought. Now that you can pinpoint the exact location of maximum stress, how would that change your approach to design? Would you make the entire beam thicker and heavier? Or would you just reinforce that one critical spot? That, right there, is the art and science of engineering. Thanks for joining us.